Hi, my name's Geordie, and the aim of this lecture is to explain to you exactly what p-values are in as simple terms as I can manage, and also just kind of to acquaint you with the general system of statistics in psychology. And the reason I'm making this lecture is that having gone through undergraduate psychology, I felt that statistics and particularly p-values were very frequently misinterpreted and mistaught. And I even had tutors who would deliberately misteach p-values because they thought it was too complicated for students to understand. And I don't believe it's too complicated. And I also think it is very important to think clearly about statistics and to understand it properly, because this is how we think about truth in science. So if you want to do that with a clear head, then you have to grapple with this stuff. So I'm taking matters into my own hands and presenting this lecture for your benefit. So as I mentioned, the crown jewel of this lecture is for you to understand what p-values are. If you can walk away from this lecture having a good grasp of that, then my work is done. All the other pieces in our lecture outcomes here feed into you understanding what p-values are, but they're all kind of necessary components for you to properly grasp what's going on. So I've split this lecture up into three parts, just to sort of signpost when you might want to take a break, but because this is a recording, you can take a break whenever you like. So let's crack on. Firstly, off the bat, what is a p-value? I want to give you a formal definition that we're going to spend the rest of the lecture exploring. A p-value is the probability of getting a result as extreme as the observed result, according to the probability distribution assumed by the null hypothesis. So there's probably a few terms in here which you're unfamiliar with, and this might seem like a lot, but we're going to spend a lot of time breaking this down piece by piece. And the first piece that we're going to look at is a probability distribution. So what is a probability distribution? Formally speaking, a probability distribution is a mathematical function which relates these two things, a set of all possible outcomes for an event and each of those outcomes' relative probability. So this will make sense if we look at an example. Imagine you flip a coin 100 times and you record the number of times that you get heads. What is the probability distribution for the number of times you get heads? Well, I can tell you that the probability distribution is going to be a shape on this graph. That is, it is a shape which relates each outcome from 0 heads to 100 heads to their relative probability. So take a moment to think about what you think this shape would look like. Assuming it's a fair coin, we'd expect this shape to be highest at 50. That is 50% of the time, or 50 out of 100 coin tosses, is the most likely outcome for a fair coin. By a fair coin, I mean it's simply that there's a 50% chance of heads, 50% chance of tails. So we'd expect the probability distribution to be highest at 50 in this case. Hopefully you can intuit that all other outcomes are less likely. So this shape is gonna drop down, but something like 48 heads or 52 heads would not be much less likely. Hopefully you're thinking about a shape which looks something like this. It's not the best drawing I've ever done, but hopefully this is what you're picturing. Something like 0 heads from 100 coin tosses hopefully seems dramatically less likely. Imagine flipping a coin 100 times and never getting heads. That would be pretty unlikely, but not impossible. So whatever this probability is over here, it's not 0, but it is much less likely than 50. And the same goes for 100. So what does the actual shape of this distribution look like? It looks like this, which is kind of close to what I drew and hopefully kind of close to what you were thinking. So let's take a moment to think about the shape of this distribution, because this is a shape that we deal with a lot in statistics, and I want to give you some intuition about it. We call this shape normal, or an approximation of the normal distribution. So the normal distribution looks exactly like this, except it's a smooth line like I'm drawing, rather than a set of bars like in our gray shape here. So what we have is a discrete probability distribution, but the normal distribution is continuous. The reason we're dealing with a discrete distribution here is because we're dealing with a number of heads from coin tosses. So that's all going to be whole numbers. That's going to be integers. We're not dealing with continuous values or fractions here. Now, technically, what we have is a binomial distribution because it's the result of a binary event, either heads or tails. Every event which influences this probability distribution is either one thing or another. But you would say it's an approximation of the normal distribution. So I want to give you a little more intuition about this normal shape, this bell curve, as it's also called, because we see it so often. Let's think about what's happening in the middle here. So as we mentioned, a fair coin has a 50% chance of heads and tails. So that's the highest point in the probability distribution. Does it seem a lot less likely to get 49 or 51 heads? Hopefully not, but a bit less likely. What about 48, 52? Less likely again. What about 45 or 55? Less likely again. And that pattern proceeds all the way down until, if we looked at something like 30 heads or 70 heads, hopefully that seems a lot less likely than getting something around 50. So that's what's happening if we spread out from the center. What's happening at the tails? Well, let's look over here at 0. How many ways are there to get 0 heads from 100 coin tosses? As it turns out, there's only one way, which is when every single one of those 100 coin tosses is tails. So there's only one possible way to get that outcome. And the same goes for 100. What about getting 1 head from 100 coin tosses? How many different ways are there to achieve that outcome? Well, there's 100 different coin tosses. Only one has to be heads. So there's 100 different ways to make that happen. What about 2 heads from 100 coin tosses? Well, suddenly the number of ways that you can do that jumps up from 100 to 4,950. That is, there's 4,950 ways to get 2 heads from 100 coin tosses. So any 2 of those 100 coin tosses can be heads. What about 3 heads? What about the number of ways to get 3 heads from 100 coin tosses? Well, that number jumps way up again to 161,700. There's 161,700 different ways to get 3 heads from 100 coin tosses. So that number keeps expanding and expanding and expanding right up until we get to 50. And then what happens? Well, at this point, there's an absurdly large number of ways to get 50 heads from 100 coin tosses. But once we get past 50, the number of ways that you can get 51 coin tosses, 51 heads from 100 coin tosses is smaller than the number of ways to get 50 heads from 100 coin tosses. So the probability distribution starts to go down in exact symmetry as the way it went up. And the pattern continues all the way out to the highest tail here. And we end up at 100, where there's, again, only one way to get 100 heads from 100 coin tosses. And I would posit that for any sufficiently complex event, that is any event where there's heaps of little events which influence the ultimate outcome, you would expect the probability distribution to be roughly normal. And a good example of that might be something like IQ. If you think about the number of things that influence IQ, it's massive. It's genetics, epigenetics, maternal factors, nutrition, exercise, education, lots of different things. So for any sufficiently complex event like that, I would argue you would expect a normal or roughly normal probability distribution. I'm going to introduce a scenario here, which we're going to keep returning to throughout the lecture. Imagine I buy a coffee for $4.80 and I pay with a $5 note, so I get a 20-cent piece as change. And I'm waiting for my coffee to be made. I walk over to my friend and I say, what do you say we have a bet? I'm going to flip this coin, and if it's heads, you buy me coffee for a week. If it's tails, I'll buy you coffee for a week. And my friend says to me, hang on a minute. How do I know that's a fair coin? You could be about to swindle me. So I say, I don't know. I assume it's a fair coin. I just got it from the cashier. But now my friend doesn't trust me. So how can we prove to my friend here that this coin is fair? Take a moment to think about how we might test this. Well, one solution would be to flip the coin 100 times or any large number of times and see if it produces heads half of the time. But of course, we already know that a fair coin won't necessarily produce heads half of the time, and we just looked at the probability distribution for that. In truth, you could get any value from 0% of the time to 100% of the time, but of course, mainly stacks up around 50. But now we have this problem where we can't necessarily expect to get heads half of the time, even if the coin is fair. So what should we do? Well, even though all values from 0 to 100 are possible, our probability distribution tells us that we can mostly expect the number of heads stack up around 50. So what we need to agree on is some threshold where if the number of heads is high enough, we'll agree that the coin is biased to produce heads. And if the number of heads is close to 50, not much higher than 50, then we'll agree the coin is not biased to produce heads. So let's say me and my friend agree that the coin is not biased to produce heads if we flip the coin 100 times and we get a result in the lowest 95% of our probability distribution. That is, if we get heads significantly more than 50% of the time, we'll agree that the coin is biased to produce heads. But if it's in the lowest 95% of this probability distribution, we'll agree the coin is not biased to produce heads. Now, where is this 95% threshold? Well, the highest 5% of our probability distribution here is from 58 up. So if you were to color in all the values to the right of this line, that would constitute 5% of the distribution. What this amounts to is a decision criteria for us. So if we flip our coin 100 times and we get something less than 58 heads, then we're going to agree that the coin is not biased to produce heads. And if we flip our coin 100 times and we get something at 58 or above, then we are going to agree that the coin is biased to produce heads. So in other words, if the number of heads we get is in the highest 5% of all possible outcomes, we'll agree that the coin is biased to produce heads. So we'll return to this example in a moment, but I want to take a break to talk about some terminology, which is going to be helpful in a second. We're now in the realm of what we call null hypothesis significance testing. This is the system of statistics that we generally practice in psychology. Not always, but generally. So what is null hypothesis significance testing? Let's break this down. Firstly, what is a hypothesis? A hypothesis is simply an explanation or prediction about something. So I'll give you an example. One hypothesis might be plants which receive fertilizer grow faster, or plants which receive fertilizer grow faster than plants which do not receive fertilizer. Another would be antidepressants decrease level of depression. So in each of these examples, there is an association between two things. So we got whether or not you receive fertilizer and growth speed, and whether or not you receive antidepressants and your level of depression. So we're talking about a relationship being present between two things. What is a null hypothesis? Well, a null hypothesis is an explanation or prediction about something which assumes no effect or relationship. So maybe take a moment to see if you can convert these two hypotheses into null hypotheses. What would the first one be? So the hypothesis is plants which receive fertilizer grow faster. The null hypothesis is simply that plants which receive fertilizer do not grow faster. What about the second example? Antidepressants decrease level of depression. Well, if you were to formulate that as a null hypothesis, you would simply say antidepressants have no effect on level of depression, or you might say antidepressants do not decrease level of depression. So that's what a null hypothesis is. What do I mean by significance testing? Significance testing is the process of evaluating the probability of an outcome according to a probability distribution. So that's more or less what we're going to be doing with our coin flip example in a moment. So putting it all together, what is null hypothesis significance testing? Null hypothesis significance testing is the process of evaluating the probability of an outcome according to a probability distribution assumed by a null hypothesis. That's a lot, but let's return to our coin flip example and see if we can apply this. So what is the null hypothesis in our coin flip example? The null hypothesis is that the coin is not biased to produce heads. And the way you might write that formally is H subscript 0. This always means null hypothesis, so H subscript 0. The probability of heads is less than or equal to 0.5. So yeah, if you were to convert this statement to a simple sort of mathematical statement, then that's what it might look like. Note that this means that the probability of heads could be less than 0.5 or less than 50%. That is, the coin could be biased to produce tails. And that's an important point we can come back to later. And the alternative hypothesis, so we've got a null hypothesis and we've got an alternative hypothesis. The alternative hypothesis is that the coin is biased to produce heads. And the way you might write that out is like this. H1, so all numbers but 0 denote some sort of alternative hypothesis. H1 is the probability of heads is greater than 0.5. So the coin is biased to produce heads more than 50% of the time. So that's what the null hypothesis and the alternative hypothesis in our example are. What is the alpha level in our coin flip example? Now, I haven't introduced you to this term yet, so I'm going to explain what it is. What is an alpha level? An alpha level is the threshold of significance required for us to reject the null hypothesis. It's also the probability of falsely rejecting the null hypothesis. So in our coin flip example, my friend and I had to decide that if we're going to flip this coin 100 times, we need to decide on some threshold where if the number of heads is high enough, we'll agree that the coin is biased. And if it's not that high, we'll agree it's not biased. So the alpha level is precisely that threshold where if the number of heads exceeds the alpha level, then we're going to agree that the coin is biased. And if it does not exceed the alpha level, we'll agree that the coin is not biased. So it's the threshold of significance required for us to reject the null hypothesis. The null hypothesis being that the coin is not biased to produce heads. And it is also the probability of falsely rejecting the null hypothesis. Now, what does that mean? Well, if we were to reject the null hypothesis, we would be saying that we're rejecting that the coin is not biased. So we're agreeing that the coin is biased to produce heads. What does it mean to falsely reject? Well, let's assume that the coin really is a fair coin. We know already that this is exactly what the probability distribution would look like right here. And 5% of this distribution is in the range where we'll agree that the coin is biased, even though it's a fair coin. So in setting this 5% alpha level, we're also setting a 5% probability of falsely agreeing that the coin is biased. Now, how do we decide on 5%? Well, that number is kind of arbitrary. In practice, sometimes it's 5%, sometimes it's 2%, sometimes it's 1%. There's a couple of factors that come into deciding on what alpha level you might use, but 5% is kind of the arbitrary norm. So what we've set up here is a null hypothesis significance test. We have a null hypothesis, which is that the coin is not biased to produce heads. We have an alternative hypothesis, which is that the coin is biased to produce heads. We have a probability distribution, which is this curve we're looking at over here. And we have an alpha level, which is 5%, which me and my friend decided on. So what do we do now? Now we run the test and we flip the coin 100 times and we see what happens. Let's imagine that after 100 coin tosses, we get 57 heads. Now, what does that mean? Well, here's our probability distribution. 57 is around about over here. Now, here's our decision criteria for whether or not we're going to agree that the coin is biased to produce heads. Now, the alpha level is 5%, which corresponds to 58 or more heads. So our 57 heads is just inside of the non-significant region. It did not reach the threshold for significance. So in practice, we're not going to agree that the coin is biased to produce heads. We're going to say that we failed to reject the null hypothesis. So this is just inside of our alpha level, which means it is not in the highest 5% of possible outcomes. So for this reason, we fail to reject the null hypothesis and agree that the coin is not biased to produce heads. Now, the wording here is interesting and it's worth maybe spending some time on. Saying that we failed to reject the null hypothesis and agree that the coin is not biased to produce heads. That's not the same as saying that we have now figured out that the coin is biased or is not biased. We're simply saying that on the basis of our present evidence, we did not have enough evidence to reject our null hypothesis. It could still be the case that the coin is biased, could still be the case that the coin is not biased. On the basis of present evidence, there's not sufficient evidence to say that the coin is biased. That's all that says. So back to p-values. What is a p-value? Let's return to this definition. P-value is the probability of getting a result as extreme as the observed result, according to the probability distribution assumed by the null hypothesis. So what was the p-value in our coin flip example? I haven't given it to you yet, but maybe think about what you would expect it would be. So let's figure out what the p-value is for our 57 heads out of 100 heads here. Here's our probability distribution, and here's a line showing what we got, which was 57. The p-value is the proportion of the probability distribution as extreme as the observed value. Now, the observed value was 57. All values as extreme as 57, that is, in our case, as high as 57, are to the right of it. So everything to the right of this blue line is what we're interested in right now. So the proportion of the probability distribution from the blue line to the right of the blue line adds up to 8.08%, or 0.0808 of our total probability distribution. So therefore, our p-value is 0.0808 or 8.08%. That's our p-value. And as we mentioned earlier, the alpha level was 5%. So our p-value is greater than our alpha level. And that's basically the only call you need to make. You just need to compare these two numbers to decide whether or not you reject the null hypothesis or fail to reject the null hypothesis. So that's an example of what we call null hypothesis significance testing. I now want to sort of generalize that process for you in 5 fairly simple steps. So if you were to explain to me how null hypothesis significance testing works, what would you say? How would you lay it out? I'll give you the first step as a hint. So the first step is you assume some null hypothesis to be true. In our case, our assumption was that the coin is unbiased. The coin is not biased to produce heads. This should actually say not biased to produce heads. What would you say the next step is? Well, we decided on a null hypothesis. Then we had to decide on the probability distribution for our event, assuming the null hypothesis to be true. And what that looked like for us is our little approximation of the normal distribution over here. What would you do next? What would step 3 be? Step 3 is to decide on a threshold for significance. So we figured out our null hypothesis, we figured out the probability distribution corresponding with that null hypothesis, and then we agreed on a threshold for significance, where if our observed result exceeded that threshold, we would reject the null hypothesis. And that's also what we call an alpha level. Fourth step is to evaluate the likelihood of our observed event with respect to our probability distribution. So that was the process of obtaining our p-value, which is simply asking what proportion of the probability distribution is more extreme than what we observed, or as extreme as what we observed, I should say. And finally, based on whether p is greater than alpha or not, we reject or fail to reject the null hypothesis. So that's the general process of null hypothesis significance testing, and that's the end of part 1. So I encourage you to take a little break now, maybe consolidate your understanding of these concepts and see if you can explain them to yourself. All right, let's crack on with the second part of our lecture. Now, so we've talked through what p-values are and all of these pieces. I want to get into the weeds a little bit further and talk about a few other important things for you to understand. So the first thing I want to talk about is 1- and 2-tailed significance tests. I want to explain what these are because if I don't, then you're going to get confused either now or later. But it's a simple concept. So in our coin flip example, we're testing whether the coin is biased to produce heads. We're not testing whether the coin is biased per se. And this comes back to the fact that my friend thinks I'm trying to trick him with a coin that's biased to produce heads, because I said to him, if it's heads, you buy me coffee for a week, and if it's tails, I'll buy you coffee for a week. So we're testing whether the coin is biased to produce heads, not whether it's biased per se. And that has implications for our hypotheses and for our significance test. What are those implications? So our hypotheses are structured like this. So the null hypothesis is that the coin is not biased to produce heads. It's not that it's not biased, it's that it's not biased to produce heads. And we're looking under that hypothesis for a probability of p is less than or equal to 0.5. Our alternative hypothesis is that the coin is biased to produce heads, and that corresponds with a probability of greater than 0.5 for heads. The other implication is we are only interested in the proportion of the distribution more extreme than what we observed in the positive direction, that is, to the right of it. So before we got a result of 57, when we looked at our p-value, we were interested in what proportion of our distribution is as extreme or more extreme than it in the positive direction. Now, imagine that rather than testing whether the coin were biased to produce heads, we're just interested in whether or not the coin were biased. So it could be biased to produce heads or biased to produce tails. Now, what would that mean for our hypotheses? Well, firstly, our null hypothesis would be that the coin is not biased. And the probability corresponding with that is simply that the probability of heads is 0.5. Our alternative hypothesis is that the coin is biased. And the probability corresponding with that is that the probability of heads is simply not 0.5. Could be less, could be more, but it's not 0.5. What would that mean for our alpha level and our decision criteria with our probability distribution? This is what it would look like. So we still have a 5% alpha level. We still have a 5% alpha level, but what we're doing is we're splitting it. So rather than looking at the most extreme 5% of the distribution in the positive direction, We're looking at the most extreme 5% of the distribution in terms of distance from the center. Distance from the center. So that captures the lowest 2.5% and the highest 2.5%. And what this would mean is we're looking for a result which is outside of this threshold or outside of this threshold to say that the coin is biased. If the coin does not fall outside either of those thresholds, then we're going to agree that the coin is not biased. So hopefully you can understand here what I mean by one-tailed and two-tailed significance tests. What we're looking at here is a two-tailed significance test because we're interested in the extremities at either tail. But what we're looking at in our coin flip example is a one-tailed significance test. So it's very important for you to understand that there's a relationship between how we structure our hypotheses and whether or not we're doing a one or a two-tailed significance test. Let's get back to our coin flip example. So we flipped the coin 100 times and we got 57 heads. So we agree that the coin is not biased to land on heads, and we proceed with our bet. But hang on a second. Does that sound a little bit strange to you? The coin landed on heads 57 times, and now we're agreeing that the coin is not biased to produce heads. It's just been demonstrated that it did land on heads more than tails. So how is it that the coin is not biased to produce heads? Doesn't it remain possible that the coin is biased to produce heads? And to explain that to you, I sort of want to introduce this concept of statistical power, which again is something which is important to understand. And statistical power goes something like this. Let's assume that the coin is biased to produce heads, let's say 65% of the time. If that were the case, what is the probability that we will correctly agree that the coin is biased to produce heads? Statistical power is the answer to that question. It is the probability of a correct rejection of the null hypothesis. Correct rejection of the null hypothesis. So let me illustrate that for you. The probability distribution we expect of a fair coin looks like this. And here is our decision criteria. Here's our alpha level. If the number of heads we get exceeds or is equal to 58, we're going to agree that coin is biased to produce heads. If it does not exceed or equal 58, then we're going to agree that the coin is not biased to produce heads. On top of this, I'm going to overlay the probability distribution for a coin with a 65% bias to produce heads. And that looks like this. So this green probability distribution is the probability distribution for a coin with a 65% bias to produce heads. You can see that it's the same shape as for the fair coin, but it's centered on 65, which is around about here. So what is the statistical power of our test? Well, that's equivalent to asking, what is the probability of agreeing that the coin is biased given the alternative hypothesis? That is, that the coin really is 65% biased to produce heads. So what we're dealing with in reality is this green probability distribution. So the statistical power is equivalent to asking what proportion of this green distribution is beyond our alpha level. That is, it is in the region of significance here. And it so happens that 92.92% of our green distribution here is beyond our alpha level. So if the coin really did have a 65% bias, there's a 92.92% chance that we're going to correctly agree that the coin is biased to produce heads. And there's also this 7.08% chance, or 7.08% of the green probability distribution here, which is in the non-significant region. That means there's a 7.08% chance that we're going to falsely fail to reject the null hypothesis. That is, even though the coin has a 65% bias, we're going to falsely agree that the coin is not biased to produce heads. And another way that you see this information presented is in a 2x2 table like this. So you can think about each row here as a different coin. Now the first row is for the coin with a 50% bias to produce heads, or in other words, a fair coin. There is a 95% probability that we will correctly fail to reject the null hypothesis. That is, we will fail to reject that the coin is not biased to produce heads, or we're going to agree that the coin is not biased to produce heads. And conversely, there is a 5% chance, even though the coin is not biased, that we're going to falsely agree that the coin is biased to produce heads. Looking at our second row here, a green row, this is corresponding to a coin with a 65% bias, so corresponding to this green probability distribution here. What is the probability that we're going to fail to reject the null hypothesis? Well, there's a 7.08% chance of that happening. So that's the case where the coin is biased, but we falsely agree that the coin is not biased. And that's what we call a type 2 error. And what is the probability for the 65% biased coin that we're going to reject the null hypothesis? So in this case, we're going to correctly reject the null hypothesis because our coin is biased. Well, there's a 92.92% chance of that happening. And this is our statistical power for our test. So we have two types of errors here. We have a type 1 error and a type 2 error. Now, as I mentioned, a type 1 error is the case where the coin is fair. So we're dealing with this gray distribution here. But we're leaving open this possibility that we could falsely agree that the coin is biased, even though it's not biased. And that corresponds to this little region here of the gray distribution. That's a type 1 error. A type 2 error is in the universe where the coin is biased. We have a 65% bias on the coin, but we falsely agree that the coin is not biased. And we had a 7.08% chance of that happening. So that's a type 1 error and a type 2 error, and they're closely attached to this concept of statistical power. The way that I sort of think about it is a type 1 error is the easier one to grasp because you don't have to assume any sort of alternative hypothesis here, like a 65% bias or a 70% bias or whatever it might be. So type 1 error, you just have to deal with this gray distribution here, and the probability of a type 1 error is simply set by our alpha level. A type 2 error it's the sequel. It's a little harder to understand. It's a little bit more complicated, and that's because it involves setting up some sort of assumption about what the actual bias in the coin might be. And in our example here, it corresponded to a 65% bias, and we had a 7.08% type 2 error rate. So statistical power is the probability of rejecting the null hypothesis given that it is false. As I mentioned, this requires you to assume what the alternative probability distribution might look like. Let's talk about the problem of low statistical power. What would it mean if the statistical power of a test were really low, such as 50% or less? Well, that would mean that even though the null hypothesis was false, there's only a 50% probability or less that you will correctly reject it. This basically makes the test meaningless. So to illustrate this, imagine that instead of tossing the coin 100 times, we just toss it 10 times. The probability for that, the probability distribution for that looks like this. You can see it's very spread out across its whole range of probabilities. And assuming our 5% alpha level again, this is what our decision criteria look like. So if we get something below 8, we're going to agree the coin is not biased to produce heads. And if we get something at 8 or above, we're going to agree that the coin is biased to produce heads. I'm now going to overlay the probability distribution for the coin with the 65% bias, and that looks like this. So as you can see, even though the green coin does have a bias to produce heads, most of its distribution is to the left of our alpha level. To be precise, 73.8% of the green distribution is to the left of our alpha level. That is, it's in the non-significant region. And 26.2% is to the right of our alpha level. So what is the power of our test here? Well, again, to remind you, the statistical power is the proportion of our alternative probability distribution, which is in the significant region. And it happens to be 26.2% here. That means there's a 26.2% chance of us correctly rejecting the null hypothesis and accepting that the coin is biased to produce heads, assuming that the coin does, in fact, have a 65% bias. That means that even though the coin has a 65% bias, there's a 73.8% chance that we're going to agree that the coin does not have a bias to produce heads. Why is the statistical power in this test so low? Take a moment to think about any parameters which you think might be at play. So what I'm asking you here is, what influences statistical power? Why was statistical power so low in this previous example? Well, let's compare our first coin flip with our second coin flip. So on the left, we have the case for 100 coin tosses, and on the right, we have the case for 10 coin tosses. In both cases, we're comparing the distributions for a fair coin and a 65% biased coin. So what's different between them? Well, the first thing, and the most obvious thing that's different, is the number of coin tosses. And we might refer to this generally as sample size and say that as sample size increases, statistical power increases. And that's because the two distributions come to overlap less. And you can see that if you compare the left and the right here. As the number of coin tosses increases, the gray or blue and the green distributions come to overlap less. They're better differentiated, which makes it easier for us to make a correct decision. The second thing that's influencing statistical power is the amount of bias in the coin. So a 65% bias is a fairly weak bias. And maybe you can imagine what these graphs might look like if instead of a 65% bias, it were, say, a 90% bias. So the green distribution on this left graph here would be much further over to the right. And there would be so much less overlap between these two distributions. So our statistical power would be much higher. The third thing which influences statistical power is our alpha level, because that's where we're drawing the line in the distributions. If we were to go for a smaller alpha level, such as 1%, then on the left here, in our left example, the alpha level would be somewhere closer to over here. What would that mean? Well, it would mean statistical power would decrease because even less of our green probability distribution here is in the significant region. More of it has been captured in the non-significant region. And what if you were to go for a higher alpha level? Let's say that we went for an alpha level of 10%. Well, that might be somewhere over here. And what would happen to our statistical power if we did that? Well, statistical power would increase because for the case with a 65% biased coin, more of that distribution is in the critical region now. So the probability of us correctly rejecting the null hypothesis has increased. But hopefully you can see that our risk of a type 1 error would increase if we did that. So what we're doing here to our gray probability distribution is lowering the threshold for how many heads we need to agree that the coin is biased. So if the coin were fair, and we've set our alpha level here at 10%, then there's an even greater chance of us falsely agreeing that the coin is biased. So there's a trade-off here between the probability of a type 1 error and the probability of a type 2 error. And that's managed by where we set our alpha level. So in sum, there are three main influences on statistical power: sample size, effect size, and our alpha level. How do we deal with this problem of low statistical power in practice? Well, firstly, if a study has low statistical power or is suspected to have low statistical power, it may simply not be worth doing. If you were to run a test which was less likely than 50% to return a true positive result, then the results are kind of meaningless. But if you are going to run a study, then before you run the study, you might increase the sample size according to what you think the effect size is. So if it's a really weak effect size, you might need to increase the sample size a lot to compensate for that and make sure that those two probability distributions are well differentiated. And also, as I mentioned earlier, you might think about where you want to set the alpha level so that you can get a fair balance of type 1 and type 2 errors. So that concludes part 2. Let's take a little break and come back and talk about common p-value fallacies. Okay, welcome back. Let's crack on with the final part of our lecture. Before we get into p-value fallacies, I want to just quickly recap what is a p-value. So let's return to that definition I gave you at the start. A p-value is the probability of getting a result as extreme as the observed result, according to the probability distribution assumed by the null hypothesis. So to return to our coin flip example, the null hypothesis was the coin is not biased to produce heads. And our probability distribution looks like this. We flipped the coin 100 times and we got a result at 57. So from that, we could figure out our p-value, which is simply all the results which are as extreme as the observed result. And that corresponded to everything to the right of 57 here. And that was 8.08% of the entire probability distribution. So that's what our p-value was. Now, if this is a one-tailed test, but if this were a two-tailed test, then you would be interested in, as far as distance from the center, how much of the probability distribution is as extreme as 57. So we would be interested in all of this region, and also on the other side, everything which is equally as far from the center as 57. So we would end up, in fact, with double this number. We'd end up with 16.16% as a p-value. All right, so let's come now to these 5 common fallacies with p-values. And these are 5 things that often you hear people say about p-values which are not true. And so hopefully by presenting them to you, I can nip them in the bud and help you from making these pitfalls. So the first, and you hear people say this a lot, is that P is the probability that the null hypothesis is true. Why is that wrong? Well, firstly, we're assuming in the process of null hypothesis significance testing that the null hypothesis is true. So properly speaking, there's no p-value which can overturn that assumption. But secondly, and moreover, the p-value represents the probability of the data given the null hypothesis, not the probability of the null hypothesis given the data. So in other words, P does not tell us about the probability of the null hypothesis being true. It tells us about the extremity of the data that we observed, assuming the null hypothesis to be true. Second common fallacy is this. P is the probability of obtaining the observed data. Why is that wrong? Well, P is the probability of obtaining data as extreme as the observed data, not identical to the observed data. Let's imagine that, for instance, we flipped a coin 100 times and we got 50 heads. 50 heads, that's right in the center here. So if a p-value is the probability of obtaining data identical to the observed data, then I can tell you that there's a 7.96% chance. 7.96% chance of flipping a fair coin 100 times and getting exactly 50. Exactly 50. That was what the p-value would be if this were true. If the p-value were the probability of obtaining data identical to the observed data. But that's not what a p-value is. A p-value is the probability of obtaining data as extreme as the observed data. Now, what proportion of our probability distribution is as extreme as 50? Well, assuming it's a one-tailed test, then we can say that 50% or 0.5 is our p-value here, because 50% of our probability distribution is more extreme or as extreme as 50 heads from 100 coin tosses in the positive direction. If it were a two-tailed test, then we would have to say that 100% or something very close to 100% of our probability distribution is as extreme as 50 heads from 100 coin tosses. So hopefully you can understand that there's a big difference between 7.96% and 50%, or 7.96% and 100% in the case of the two-tailed test. So the third fallacy I want to talk to you about is this idea that a small p-value indicates a large effect size. Why is that wrong? Well, you can get a small p-value with an effect size of 0. So imagine we have an effect size of 0 with our coin. So in other words, we have a coin with no bias. It's a fair coin. It's entirely possible that we could get a rare result, even though the coin is fair. We could get 80 heads from 100 coin tosses, and we'd end up with a really small p-value because this proportion of the distribution is very, very small. So we would have a small p-value with an effect size of 0. Therefore, a small p does not necessarily indicate a large effect size. I'll give you a second reason why that's wrong. You can get a small p with a small effect size. It doesn't have to be an effect size of 0. It could be a small effect size, especially if the sample size is large. So let's compare two probability distributions. The distribution for 10 coin flips on the left here, and the distribution for 1,000 coin flips on the right. Let's imagine we have a small effect size, or in our case, a small bias in the coin. Let's say we have a 60% bias to produce heads with our coin. Well, if we flipped a coin 10 times and we got 6 or 60% heads, then we would have a result here. That would correspond with still a large p-value, because the proportion of our distribution more extreme than that in the positive direction is quite large. So we would have a fairly large p-value, even though we have a small effect size. Compare that to the situation where we flip the coin 1,000 times and we get heads 60% of the time. Well, of course, 60% of 1,000 is 600. So our observed result would be here, and our p-value would be constituted of this proportion of the distribution here. So we would end up with an incredibly small p-value, even though it's only a 60% bias in the coin. So you can get a small p-value with a small effect size, especially if the sample size is large. Therefore, a small p-value does not necessarily indicate a large effect size. You can get a small p-value with a small effect size, especially if the sample size is large. The fourth fallacy I want to talk to you about is that if p is less than alpha, that means the null hypothesis is false. So let's just remind ourselves of what an alpha level is. That's the level of significance that we need to see to decide to reject the null hypothesis. In our coin flip example, we set that at 5%. Why is this fallacy wrong? Well, p can be less than alpha when the null hypothesis is true. And that's what we called a type 1 error. So remember, let's assume that the coin is fair. We could still get a result beyond our critical threshold here, and the probability of that is set by our alpha level. So it's entirely possible that the null hypothesis is true, even though our p-value is less than alpha. So that's why this fallacy is false. And that's the entire principle of a type 1 error. Finally, our fifth fallacy here is that if p is greater than alpha, that means the null hypothesis is true, and by extension that the alternative hypothesis is false. The reason why that's wrong is simply that p can be greater than alpha without the null hypothesis being true. So that would be the case where P is larger than 5%. So it's in our non-significant region here, but the coin actually is biased. So we're going to falsely agree that the coin is not biased to produce heads, and that's a type 2 error. And that's why if P is greater than alpha, it does not necessarily mean that the null hypothesis is true. And that concludes the third and final part of the lecture. If you got all the way through, then I hope it was worth your time. You can check your understanding of all these different components, and hopefully you can explain to yourself or to other people what a p-value is, because that really is, as I mentioned, the crown jewel of our lecture here. And all of these other pieces are helping you to understand what a p-value is. So please check your understanding. If you can walk away knowing what a p-value is, then that's great. My work is done. I hope this has been useful to you, and thanks for watching. I encourage you to contact me if you have any questions or otherwise. Thank you and all the best.